what we're going to look at are one-sided limits. And we're going to use one-sided limits to be able to tell if a limit actually does exist or not. Okay? And as an example to figure out what one-sided limits actually are, we're going to take a look at this. Does the limit as x approaches 0 of the absolute value of x over x exist? Okay? Now, the absolute value of x, if you look at y equals the absolute value of x, that's actually like a piecewise function. Okay? So it looks like this. Whoops. Okay? It's a piecewise function, and it looks like this. That's not the function that we're looking at, by the way, right? Because we're looking at the absolute value of x over x. But you have to remember that the absolute value of x equals one of two things. It either equals x, right? So the absolute value of 3 is what? 3. So if x is positive, the absolute value of x is just equal to x. So it's equal to x if x, whoops, I should have done that, sorry. If x is greater than or equal to 0. Okay? If x is positive, the absolute value of x is just x. If it's negative, though, the absolute value of x is equal to negative x. Oh, sorry, it's equal to x if x is let me just, what am I doing here? Okay. I'll give myself some more room. Hopefully you guys aren't like super fast writers and are not keeping up with me, and then you have to erase everything. The absolute value of x is equal to x if x is positive, and negative x if x is negative. Right? So if you think the absolute value of negative 5 is what? 5. So negative 5 is 5. Okay? If you look at the graph, when x is negative, you're looking at the function y equals negative x. When x is positive, you're just looking at the function y equals x. Okay? Now, this is not that function. This is a different function. But we're going to use this fact to kind of make a table of values to see what this would look like. Okay, so let's make a little table of values. Okay, so let's say x is 3. Okay, absolute value of 3 is what? 3 over 3, 1. Absolute value of 2 divided by 2 is 1. The absolute value of 1 divided by 1, 1. Right? And the reason, by the way, is this is, that's where the 1 comes from, right? This one is, I didn't give myself very much room, but the absolute value of 2 over 2. Okay? The absolute value of 0 over 0. So this is 0 over 0. What do you think about that one? What would we call that? Okay. So When you have the value 0 over 0, undefined is a really good thought, but this is actually called an indeterminate. Okay, and that's a term that we use in calculus. And an indeterminate is a term that we use, and this is not the only indeterminate, by the way. There are other ones. Another example of an indeterminate is 0 to the power 0. Okay? Another example of an indeterminate is infinity over infinity. An indeterminate is where you don't really know what's going on. And the reason why this is an indeterminate is because, and I'm going on a bit of a tangent here, but that's okay. 0 over 0 can be written as 0 times 1 over 0. Yeah? Okay. So the issue is we don't know which of these two things takes precedent. If the first one takes precedent, then the value of this is 0, because 0 times anything is 0, right? If the second one takes precedent, then this is undefined, because 1 divided by 0 is an undefined value. Okay? So this is called an indeterminate. Sometimes when we're looking at limits of indeterminates, sometimes those limits exist, and sometimes they don't. And we'll look at more at that as we go through the course. Okay? But there are more than just one indeterminates. Another one, for example, would be 0 to the power 0. Okay? And the reason that that one's an indeterminate is because of this fact. We know that 0 to the power anything is 0, right? 0 squared is 0. 0 cubed is 0, right? On the other hand, we know that anything to the power 0 is 1. So which one is it? That's why that one is an indeterminate. Okay? All right. Now, moving along, let's look at this one. Oh, I'm sorry. What am I doing? I put the same values on. There we go. That's better. -1, -2, -3. Okay. Absolute value of -1 over 1. -1. This is absolute value of -1 over -1. What's the value of that? -1. Because the absolute value of -1 is 1, divided by -1 is -1. Okay? This guy, I really should have spread this out some more, is going to be the absolute value of -2 divided by -2, which is -1. And then this guy is the absolute value of -3 divided by -3, which is -1. Okay? So if we look at this graphically, what we have going on is this. Here's 1, here's -1. When x is positive, the value of the function is 1. When x is negative, the value of the function is -1. And at 0, we don't know what's going on. There is no value of the function. There's like a hole. It's not even a hole because these 2 points are kind of disconnected, right? There's a complete discontinuity in the graph. Okay? Now, this brings up one-sided limits. We can talk about the limit of the function as x approaches 0 from the left side, and we can talk about the limit of the function as x approaches 0 from the right side. Okay? Now, the way that we would denote that is this way. The limit as x approaches 0 from the left, we use a little negative sign to say that we're coming from the left of the absolute value of x over x is equal to -1. Because as you're getting closer and closer to 0, your function approaches -1. Okay? From the right side, if you're approaching 0, x is approaching 0 from the right side, the limit as x approaches 0, to show that we're coming from the right, we use a positive sign of the absolute value of x over x is equal to +1. Okay? Now, if the limit from the left doesn't equal the limit from the right, the limit doesn't exist. Okay? The limit from the left must equal the limit from the right. So in other words, if you look at my two hands and they're coming together, they have to meet. If it goes like this, there's no limit. Okay? The other thing is that I have to have my hands coming together from two directions. Okay? I can't just have one side come to a point. So if you have like an end point on a graph, for example, there's no limit at that point. Okay? Because at an end point, the function wouldn't approach that point from one of the two sides. Okay? So this is important. I know it doesn't come clearly on the smartboard, but hopefully it comes out clearly in your notes, right? If limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then the limit as x approaches a of f of x does not exist. Okay. So we're going to kind of explore this using this graph below. Okay? So find the following limits for the graph below. So first we're going to look at f of -4. What is f of -4? F of -4 doesn't exist. There's a hole. F of -4 does not exist. Okay. What is the limit as x approaches -4 from the left? As x approaches -4 from the left of f of x, what's that limit? Yeah, 2. What about as x approaches -4 from the right of f of x? What's the limit? Yeah, it's also 2. Because they're coming together and they're approaching the same value, right? They don't actually have to reach that value, but they can get infinitely close to that value. That's also 2. Okay, so then what is the limit as x approaches 4 of f of x? Yeah, it's 2. As long as the left-hand limit equals the right-hand limit, the limit exists. Okay, let's look at this one. What is f of 6? Yeah, it's 2, because there is a point 6, 2. So f of 6 is 2. Okay, What's the limit as x approaches 6 from the left? Yeah, 5. Yeah. As x gets close to 6, the function gets close to 5 as you're coming from the left. Okay? When you're coming from the right, when you're approaching 6 from the right, what does the function approach? When you're coming from this direction, what does the function approach? 5. Yeah. Okay. So then, what is the limit as x approaches 6 of f of x? What would the limit be? 5. Yeah. Okay. The limit does not have to equal, the limit as x approaches a of f of x does not have to equal f of a. They just have to approach the same point. If they're approaching the same point, if they're approaching the same value, that's the limit. Okay, let's do one more. Okay, what is f of 1? 4. Okay, what is the limit as x approaches 1 from the left? 4. Yeah. What is the limit as x approaches 1 from the right? -2. What is the limit as x approaches 4 of f of x? Doesn't exist. Correct. Right. Okay. All right. So we're going to do a couple of examples in the next 2 pages. Now, these would be questions that I would expect that you would be able to do without any graphing technology, right? So you have to kind of remember how to graph basic functions and what they're going to look like, okay? So find the limit as x approaches 2 from the right of the absolute value of x minus 2. So the function, the absolute value of x, is that sort of v thing, right? If I'm looking at the function absolute value of x minus 2, what's going to happen to that graph of the absolute value of x? Yeah. Shift down by 2? Almost. Yep. It's going to shift right by 2. Yeah. So this is going to look like this. Okay. All right. So as x approaches 2 from the right, what is the function approaching? 0. Yeah. Okay. Here's another one. What is the limit as x approaches 7 from the right of the square root of x minus 7? And what's the limit as x approaches 7 of the square root of x minus 7? Okay, so your basic square root of x function looks like a parabola sideways, but just half of it, right? So that's y equals square root of x. Okay, if we're looking at the square root of x minus 7, what's going to happen to that graph? It's going to move right 7 units. Yeah, so this is that function. Okay, so as x approaches 7 from the right, what is that limit? Yes, it's 0, because the function is getting closer and closer to 0. Okay. What's the limit as x approaches 7 of the square root of x minus 7? What do you think? Yeah. Doesn't exist. Why not? It's an endpoint, yeah. So for the limit to exist, it has to come from both sides. Okay? Okay? This is an endpoint. Okay? So what we're going to talk about next is continuity and discontinuity. Because if a function's continuous, limits are easy, right? Because the limit is just the value of the function at that particular x point. Where things get more complicated, though, is where there is a point of discontinuity. Okay? So there are a couple situations that you can have with discontinuity. Okay? You can have something where f of a is not defined. So that might be a hole in the graph. So this is a. And this is f of a. Okay, that would be a point of discontinuity. Now, this point of discontinuity has a limit. Because as you approach a, there's convergence in the function, in the value of the function. Okay? The second situation that you can have is that the limit just doesn't exist, right? So that's where you might get a vertical asymptote, right? So if you look at this, something like this, there's no limit there. Because if this is a, as the function approaches a from the left, the function's approaching negative infinity. And as you approach a from the right, the function is approaching positive infinity. Okay? So it might look like that, but it also might look like this, actually. It could also just look like this, where this is a, and you might have something like this. And then that. Okay? The limit of that also, at point A, the limit does not exist there either. Okay? Because again, as you approach A from either direction, there is not convergence in the function, in the graph. Okay? And then the other thing that can happen is that the limit as x approaches a of f of x doesn't actually equal the value of the function at a. So that's where you might see something like this, where, let's say there's a hole here, and then this is a, but the point is down here. Okay, so the function is defined at a. It's not continuous at a, though. And the value of the function is not the same value as the limit of the function, because the limit at a is whatever this is right here, right? This over here is the limit at x as x approaches a of f of x is right here. Okay. Any questions so far? Are you guys still writing down? No? Okay. So what we're going to do next is we're going to look at some piecewise functions. Have you guys have seen piecewise functions before or no? Have you? I can't remember. I haven't taught 30-1 in a couple years. Yes or no? No? Okay. Sweet. Okay, so a piecewise function is basically, as it sounds, like you're piecing different functions together over different sort of domains. Okay, so this is a piecewise function. We're told that f of x is equal to x squared minus 1 if x does not equal 0, or 3 if x equals 0. So those are the conditions. If x equals 0, f of x equals to 3. Okay, so we could put that point in, actually. When x equals 0, f of x equals 3. If f of x doesn't equal 0, if x doesn't equal 0, then f of x equals x squared minus 1, which is just a parabola that has been shifted down 1 unit. Okay? So what that means is that there's a hole right here. Right? Because when x equals 0, it does not equal x squared minus 1. It equals 3. And then I can put it in my points, so 2 up 4. Right? So it's going to look like this. Does that make sense? Yeah? Okay. So where is f of x discontinuous and why? What is the point of discontinuity? Where is it discontinuous? Yes, it's discontinuous at x equals 0. Since, why is it discontinuous at x equals 0? Like thinking back to what we just talked about on the previous page, around these different types of discontinuity. What sort of language would you use to describe this type of discontinuity? Which one of these three is it? Do we have a limit at the point of discontinuity? The point of discontinuity was when x equals 0, right? Is there a limit there? Is there a limit when I approach from the left and from the right? Yes. Okay, so there's a limit. Okay. So we do have a limit. Okay. Is the function defined at the point of discontinuity? Do we have a defined value of the function when x equals 0? What is the value of the function when x equals 0? 3. Okay, so it's not the first one. The limit does exist. Is it this one? Where the limit as x approaches 0 of the function does not equal f of 0? Yeah, it's this one, right? So since the limit as x approaches 0 of f of x does not equal f of 0, right? Because this one is -1, and this one is 3. Okay. Let's do another piecewise function. Okay, so graph f of x if f of x equals x squared if x is greater than 0. Okay, so let's just do that part. If x is greater than 0, okay, f of x looks like x squared. So that's like a parabola, right? Now it's greater than 0, so this is kind of like an open circle. And then so on the right-hand side, it just looks like y equals x squared. So I've got a point at 1, 1. I've got a point at 2, 4. I've got a point at 3, 9. Wait, 2, 4, 6. Yeah. Okay, so this is one side. That's this piece. Okay. F of x is negative x if negative 2 is less than x, which is less than or equal to 0. Okay, so negative x is a linear function, and it's like going that way, negative slope, right? So starting at negative 2 is exclusive because the inequality is just a less than, not a less than or equal to. So this one is going to be an open circle. And then the 0 is inclusive. So that endpoint is going to be a closed circle. And it's just between those two x values. Now this gets colored in. So actually, because these two endpoints are the same, there's no discontinuity there. Okay, so this is actually continuous at x equals 0 because this value is the same as that value. Okay, so we did that one. And then f of x equals negative 2 if x is less than 2. Less than negative 2, sorry. So that's here, and f of x equals negative 2 is just a horizontal line. Okay? This one is exclusive, so that gets an open circle. And that looks like that. Okay? All right. So where is f of x discontinuous? So discontinuous at negative 2. Yes. So these piecewise functions are not always discontinuous wherever they join, because or wherever sort of the intervals join, because sometimes the endpoints connect, right? Like this one did. So it's discontinuous at x equals negative 2. How come? Why is it discontinuous at negative 2? Yes. Neither side of the function, sorry? Okay, yeah, so one reason is that f of negative 2 does not exist. Okay, so Okay, so that's one reason. There's another thing that you can say.
Because they don't equal each other?
Well, they're not. What doesn't equal each other?
Well, the first line, there is the one above.
Yeah?
Yeah, that one is continuous, and therefore has a limit. Or no, it has a limit. They both have limits, right?
Well, they both have limits from either side.
Yeah, but they don't.
Are the two limits from either side the same?
No, that's why.
No. Yes. So the other thing that you can say is that the limit as x approaches -2 from the left of f of x does not equal the limit as x approaches -2 from the right of f of x, or the limit as x approaches -2 for f of x does not exist. If the limit doesn't exist, there's going to be discontinuity. All right. I think we're done. We're done for today.